Welcome back, everyone. Our next talk is quantum computing, the reality behind the headlines with Richard Murray. And quantum computing, as you all know, is an emerging answer to the world's data challenges, but so far we haven't yet achieved the thousands of qubits that are needed to solve some useful problems. In his talk, Richard will summarize the state of the art and how ORCA Computing are looking to build quantum computers with a completely new approach that leverages single units of light, optical fibers, and off-the-shelf telecoms equipment. Dr. Richard Murray is the CEO of ORCA Computing, a startup with a pioneering approach to quantum computing. Richard is also one of Europe's foremost experts in the commercialization of quantum technologies. Richard, thank you so much for being here with us.
Thanks, Stefan. So really happy to be here. Thank you so much for inviting me. So as you just said, hi, my name's Richard Murray. I'm CEO of ORCA Computing, a brand new quantum computing company based in London in the UK. And what I'll just do in my quick talk is summarize the quantum computing field, particularly the quantum hardware field. So where things are currently at, hopefully give people a good idea of sort of how much potential quantum computers have, but also where they are right now, and where they are right now is that there are toy systems available, but those systems still need to be developed before they're truly useful and truly realize the potential that people believe they have. So what is quantum computing? Why are people so excited about it? So I believe many people in this audience probably know this already. There are a number of very challenging, complex problems which classical, conventional computers that we have currently really struggle to get traction with, highly intractable. So these are things like optimization, so finding the minimum path between two roots, differential equation solving, linear algebra, factorization. And of course, these problems affect many broad range of industries and use cases. So currently, if people want to try and undertake material and drug discovery, that's incredibly challenging to do with classical computers. If people try to optimize very large problems, so financial portfolios, for example, it's very hard to find the ideal solution from those portfolios. Many aspects of computational fluid dynamics are really struggling to they struggle to solve problems once they reach a certain scale. And there are many logistical problems. So, if I want to find the minimum route between here and where I live in a place on the south coast of England, it's very hard to find the absolute optimal minimum path. So lots of different, very challenging problems, lots of very big applications in UK use cases in industry that currently are not unlocked. So the world major ICT companies are really interested in looking at new computational platforms that can help solve these very complex problems. And quantum computing is, of course, one of those. And from a slightly different perspective, there's a huge energy cost in current computation. So currently, high-performance computers typically require as much energy to run them as they do to buy them. So your operational costs over a 5-year lifetime currently equal the amount that it currently costs to buy a high-performance computing system. And that is also one of the elements which makes them highly difficult to scale. So people have said that it's $1 trillion market by 2030. I think that's maybe a little bit ambitious, but there are huge opportunities available for new computing platforms like quantum. So why aren't quantum computers with us now? Why aren't people really using quantum computers? Why aren't they integrating them within their current business? Well, you probably know that there are a number of different hardware players out there. So we heard earlier from IBM. There are also Google, Rigetti, D-Wave, working with superconducting qubits. There are also ion-based qubits. So the leading companies there are IonQ, Honeywell, and I believe we'll hear later from Winfried Hensinger from Universal Quantum. There are also Microsoft and other lead players. But currently, as promising as those platforms are, they currently struggle to solve some of the provide the real resources that can be used and made useful by the growing emerging quantum software community. So above those guys, you can see a number of logos from quantum software companies currently designing software to run on quantum computers. But the simple fact is that until those software providers have systems which have properties like enough qubits, enough quantum bits, a high enough gate fidelity, a high enough connectivity, a fast enough system, and then on the commercial side, a suitable manufacturability, a wide number enough applications, the possibility of integration. Until those critical, what we call the quantum gap challenges can be addressed, you won't see quantum computers be truly used to realize their future potential. And so, sorry. And so, I like to say that even though there are really promising platforms out there, superconducting, trapped ion, and photonics, we currently are in the stage where there is no obvious winner. It's a really exciting landscape at the moment where there are a number of different platforms vying for lead position. But all of those platforms need to overcome some challenges in order to show that they can scale up to useful numbers of qubits, so hundreds or thousands of qubits. And I hope those platforms wouldn't mind me saying that they have lots of potential, they have lots of advantages, but also they have some disadvantages associated with them, challenges that need to be overcome. So superconducting qubits from players like Google, Rigetti, IBM, they have demonstrated quantum supremacy, a fantastic achievement for the field. But there is an ongoing challenge of crosstalk. So it's difficult to stop each qubit talking to each other qubit in a way that you need to ensure complete sort of controllability of each of your qubits. So the more qubits you add, the more crosstalk increases and the more noise you create as well as signal. That's a challenge that the superconducting community need to overcome. For trapped ion systems, they have demonstrated very high quality operations and a very high quantum volume, but typically those systems are somewhat slow. They are changing, but they're slower than the other platforms, and somewhat bulky. Silicon photonic systems are very, very fast, but the common challenge is that they require many, many components. You need millions of components to deliver just a smaller number of qubits. So there's no current winner. So the world are currently sort of holding their breath to see which of these platforms will emerge as the leading player. Just to turn on to ORCA Computing for a second. So we started a year ago with what we like to say is the world's first fiber optic quantum computing platform. So rather than choosing to work with these sort of bespoke, very individual devices, ORCA have designed a platform that allows us to work with optical fiber, which is a sort of very common material used to define the internet. And really inherent to, I think, ORCA's platform is this idea that sort of unlike other quantum computing platforms, where you might be designing specific circuits, chips that define your qubit, for photonic quantum computing, your qubit the information is defined, is carried by a single photon. So it's a very fundamental sort of object, which is sort of quite robust against noise. So that's the advantages of working with photons. The advantages of working with optical fiber are that ORCA can work with off-the-shelf components. So we can use telecoms laser systems. We can develop a lower cost platform because of that. And ORCA are really trying to build a quantum computer for less capital, less investment. We believe that fiber optics is a very scalable platform. So your internet is firstly very scalable, and you can plug and play different components to allow systems to scale. And related to that is also reconfigurable. So we like the fact that when you're designing these quantum systems, you sort of want your quantum circuit to try and represent the problem that you're trying to solve. Optical fiber allows you to sort of reconfigure, plug and play optical fiber elements in order to reconfigure your circuit so that it represents the problem you're trying to solve. We also like to think it's compatible with networks, so you can, optical fiber the information is already being processed in optical fiber, so you can use it to carry to plug into optical fiber networks. And really to emphasize, what we're really trying to push within the company is to try and do quantum computing with less resource, meaning fewer numbers of components, less capital, less bespoke design. And this is challenging because the whole field is being challenged, and to try and do it with less resources is even more challenging. But our belief is that unless you can try and do quantum computing with less resources, you will always run into scalability problems that will stop you reaching the true potential of quantum computing. So what does quantum computing with photons look like? I think it's always useful to sort of boil it down to how it actually forms a computer, how you can actually use it to form computational logic. So for photonics, a qubit, a quantum bit, is defined by whether a single photon is in either one optical fiber or another. So one bit is defined by two optical fibers, and which optical fiber the photon is in defines the unit of information a bit. So of course this is quantum. So unlike sort of classical, where your photon is within either one optical fiber or another one, your qubit can exist within both optical fibers. So one single photon can exist within two optical fibers at the same time. And then the way that we can perform gates, so you can perform a Hadamard gate or a Z rotation by performing operations that are probably familiar to the optics community, by performing things like beam splitters, so by mixing together two optical fibers and separating them out again, or by phase modulation. And what's nice about ORCA and our approach is that those operations are capable with off-the-shelf components. So you can buy fiber beam splitters, you can buy fiber phase modulators. So our dream, our belief, is that we'll try and do quantum computing using these components. Okay, so I made it sound sort of simple, right? So you take a bunch of optical fiber components and you plug them together and you've got a quantum computer. What on earth is the problem? Why don't you just do it? Well, yeah, we are doing quantum computing. It's not straightforward. I think people have described it as one of the biggest engineering challenges of our lifetime. And the challenge for photonic-based approaches is two things. It's ensuring synchronization of photons. So because your information is being carried by your photons that need to arrive at the right time in order to be able to be involved in operations, they need to be, those single photons, they need to all be in the same place at the same time. So they need to be synchronized in order for them to be able to undertake operations. And the second challenge is loss. So if you have a single photon, if your information is encoded in one single photon, as you sort of couple in and out of different components, if you happen to lose that single photon, you've lost a unit of information. So your sort of error processing will have to compensate for that. So two big challenges of photonics. So you need synchronization and you need low loss. ORCA's approach, so our remedy to those challenges, is this quantum memory which we've developed. So ORCA's, what really defines ORCA is a proprietary quantum memory device. So that essentially allows you to store and retrieve single photons on demand. So you can park your single photons. And for those of you familiar with sort of how classical computers work, your ability to use memory to buffer operations is what defines sort of error correction in computing systems. So by buffering quantum operations, you can allow them to overcome, essentially you can allow them to overcome this synchronization problem, and you can also allow yourself to buffer out noise, loss of photons, and other difficulties like this. So our quantum memory is really exciting. It's a thing that allows us to work with optical fiber and defines our platform, and it then allows our ability to work with off-the-shelf fiber components. Even more exciting and really pushing out this idea about being resource efficient, ORCA's really pushing on this idea of time domain computing. So typically one device is something that defines a qubit. So you have one superconducting qubit, you have one ion, and that is the thing that gives you your qubit. Therefore, if you want to have many qubits, you need many devices. The nice thing about photonics and single photons is that the thing that's defining your qubit is a photon, and you can actually have many photons within one optical fiber. So flipping things on its head, rather than having lots of single photons, lots of optical fibers, lots of sources, lots of detectors, which obviously is a huge resource constraint, resource requirement. you can have just one source, one optical fiber, and one detector. And within that system, you can have many photons, so many qubits. So this is our current short-term plan, hoping to drive down the number of components and the device cost. But I will recognize that the real true power of quantum computing comes when you achieve fault tolerance, so your ability to correct errors. And every platform has its own roadmap for fault-tolerant quantum computing. I won't scare you too much with the diagrams, but ORCA's, these fault-tolerant machines are very complex, but at the same time incredibly powerful. And ORCA has this roadmap of using its components and its quantum memory in order to achieve fault-tolerant quantum computing. So, the last thing I'll say before handing over for questions and answers is something about the team. So, I'm tremendously proud and thankful for the team that we've built up here in the UK around our technology. So there's myself, I worked as a technology consultant and also as part of the UK government, but also have a PhD in quantum. I'm leading the team here. One of my other co-founders is Professor Ian Walmsley, who's Provost of Imperial and inventor of, a leader in ultra-fast quantum optics and inventor of the SPIDER technology. But also sort of shout out to some of the other team members. So Josh Nunn, who's our CTO, who invented the quantum memory, Camille Bradler, who is our lead architect, Christina, who's our COO, and Michael Pereno, who's leading up corporate strategy. So with all of that, there's a whistle-stop tour into quantum computing, ORCA, photons, and everything else. So I'll just summarize by saying, ORCA, we're really excited. We've got a unique approach towards photonic quantum computing using our proprietary quantum memory technology, leveraging plug-and-play telecoms components with a world-class team and a capital-efficient business model.